Hi guys, so today we have converse of basic proportionality theorem. Okay, now what does converse of basic proportionality theorem state, right? So it states that if a line divides any two sides of a triangle in the same ratio, the line must be parallel to the third side. All right. So here what do we see is that they are saying, okay, that in this figure, right, ABC is a triangle and AP upon PB is equal to AQ upon QC. As we can see in the given, a triangle ABC, okay, and a line L. So this is the line L intersects AB at P and AC at Q, okay, and makes sure that AP upon PB is equal to AQ upon QC. This is opposite to what we did in basic proportionality theorem. If you haven't watched my previous video, okay, on basic proportionality theorem, the concept have been explained to you all, okay, already. So which is why in this video I have picked up converse of basic proportionality theorem. So most of you find this a bit tricky and confusing, so I have picked up this to follow the basic proportionality theorem, correct? Now here this is very interesting in the sense that they say that you prove, what do you prove? That PQ is parallel to BC. In that case, PQ was already parallel to BC. We had to prove this. We had to prove the line segments, okay, on AB, say AP upon PB, was to be made equal to, or was to be proved to be equal to AQ upon QC. Got it? So that was basic proportionality theorem. In short, we also call it Thales theorem. But this is converse of basic proportionality theorem or converse of Thales theorem. Right? So here our contention or thing is that we have to prove that PQ is parallel to BC. BC is the third side of triangle ABC, and AB and AC are being divided into two parts, such parts so that AP upon PB, okay, and AQ upon QC have the same ratios, or they are cut in the same ratios. Clear? Now let's go ahead with the proof. How do we prove that PQ is parallel to BC? We can't directly say it. Okay? So now we try and rationalize and try to convince by saying ki, okay, so if PQ is not parallel to BC, there must be some line that must be parallel to BC, isn't it? So that is a possibility. So let's assume that PR is parallel to BC. So if PR is parallel to BC, and as per basic proportionality theorem, not converse, basic proportionality theorem, you must go and watch my basic proportionality theorem video, okay, to get the clarity of things, okay. So as per basic proportionality theorem, if a line, say PQ, is parallel to BC, in that case AP upon PB will be equal to AQ upon QC, right? So here we haven't, okay, got the declaration that PQ is parallel to BC. We are therefore taking through construction another line PR to be parallel to BC. If PR is parallel to BC, automatically we know that AP upon PB, okay, must be equal to AR upon RC, correct, to justify basic proportionality theorem. All right. Now let's go ahead and get deeper into the proving, right? So we have, let's assume PQ is not parallel to BC. PQ is not parallel to BC. Then what? Then there must be another line parallel to BC. So let's assume that PR is parallel to BC. By basic proportionality theorem, we get that AP upon PB is equal to AR upon RC. Am I right? So this is what we derive out of it. But here is the thing that we have to notice or take cognizance, that AP upon PB is already proved to be equal to AQ upon QC. AP upon PB is given as equal to AQ upon QC. So if AP upon PB is equal to AR upon RC as well as AQ upon QC, these two must be equated. They must be equal to each other, isn't it? Which is what I have written here. Okay. So as a result, we can equate these two. So AR upon RC is equal to AQ upon QC, correct guys? So if they are equal, so we have to go ahead to further prove that R and Q must be overlapping or they must be coinciding. So for that we have to take the step necessary to reach there, and which is we add 1 to both of them. We add 1 to both sides, to LHS, that is left hand side, and to RHS on the right hand side. Correct? And having found RC as LCM here and QC as LCM here, we get AR plus RC. Okay? Because this has a denominator of 1. This also has a denominator of 1. So as a result, we have AR plus RC here and AQ plus QC here. Got it? And AR plus RC indirectly means AC. And AQ, this one, AQ plus QC indirectly means AC. Having got the sum of this two, okay, equals to AC and AC respectively, we know that if we cancel them, RC will go to sit that side and QC will come and sit over here, which means RC is equal to QC. So if RC is equal to QC, means what is R doing there? It has to be sitting on the point where Q is, which means what? That this is only possible if R and Q are coinciding points, right? So therefore we know now that if PR was deliberately made parallel to BC and PR stretches, okay, almost overlapping over PQ, or R and Q are on the same position, it means that PQ is parallel to BC and hence proved. So this was what we had to prove. PQ is parallel to BC. Alright guys. So this was a smooth walk. Okay. It wasn't difficult. Neither was a rocket science. It is very easy. Just that the converse thing is not liked generally by us. So we get a little taken aback by this thing, but it's very easy. Okay. So I hope you have understood. So in case you haven't, then you can always write in the comment section wherever there is a doubt, but you can also pause the videos and go through each and every step, okay, 1 or 2 or 3 times, so that you achieve your clarity. Okay guys, so have a great day and thank you for watching my video. Okay, but please do go to the previous video to start from here and then come back to this. Okay guys, So this two, okay, theorems are quite okay important from exam perspective, so that you can prove riders on the basis of these theorems, right? So bye bye for now, see you soon, okay, with another interesting concept. You can see my whole playlist, which consists of a number of such interesting concepts. Bye bye.